Hello, everyone. Welcome to another Sunday tutoring session with me, Melissa Maribel. So happy to see that everyone is joining in, and we're focusing on a new topic today. And every single Sunday, we'll be getting into more and more detail with different concepts of chemistry just to really guarantee that you will not only pass, but succeed if you want to get an A or a B, or if you do decide to get a C, so be it. But I'm always trying to get all my students to get at least a B or an A. And also wanted to talk about why I'm doing this, why every single Sunday I am committed to being here within this hour and this time frame to really just give you my knowledge and share my knowledge of chemistry and what I've learned throughout the years, and all my, my little tricks and tips on chemistry in general. So the reason why I'm doing this is as a thank you for subscribing, and really appreciate that you guys are such great subscribers. You're viewing and commenting on everything, and I love that participation. So as a thank you, I'm doing these Sunday sessions. Also, something really cool is if you guys help me get to 10,000 subscribers. So if you share with any classmates, or if you know anyone that can really benefit from these tutoring sessions, or really just my channel in general, please share my videos to get us to 10,000 subscribers. And if that is the case, if we get to 10,000 subscribers, I will do an 8-hour live tutoring session. Yes, you heard correctly. 8 hours live, where you can ask your questions and us just really, really get down to all the other questions that you have, and to really prepare you for your finals so you can succeed again, because I know the chaos of finals. I live it every single semester with my students, and I've dealt with it myself before as a student previously. So really help me to get there, guys. And let's jump right into today's topic of different geometries. So we're going to have several different types. So we're going to have electron geometry, molecular geometry, and also something known as Vesper Theory. So we'll go over all of this, as well as polarity. So what we'll be doing towards the end, so make sure to stick around towards the end, we're going to be focusing on polarity and a really cool trick as to how to know if something's polar versus non-polar. It's a really awesome visual that incorporates just bodybuilding. So tune in for that. Okay, so let's dive right in. And we'll focus on, we'll focus on just the differences of our typical Lewis structure that we've seen before, as you can tell here. So last week we were doing just your regular Lewis structures and how to draw them and how they're bonding to other elements to form this structure or compound as a whole. Now, today we're going to focus on something known as Vesper Theory. And what Vesper Theory indicates or stands for is our valence shell electron pair repulsion. Okay, I know it's a mouthful. So our Vesper Theory here is really just showing you how the structure or the molecule actually wants to be drawn. So when it's talking about electron pair repulsion, note that electrons are negative, and electrons, as they come together, they want to repel against each other. That's why it's called repulsion. So in our case, we wouldn't necessarily have this sort of structure. We would actually have hydrogen all spaced out, or all the bonds properly spaced out, so they can repel each other. So once again, Vesper Theory as a whole is really just valence shell electron pair repulsion, where our electrons are repelling away from each other. All right, so there are several different types, which we'll get to. You probably are starting to see different types of charts like this in class. Or if you haven't just yet, you will get there. This is specifically the different types of Vesper Theory, and you'll see that everything on this table is something that you will have to know, just is pretty much the proper way to draw different Lewis structures in Vesper Theory. And we'll get to that. The next portion of this is really diving into different types of geometries and what in the world they are. All right, so we're going to have two different types of geometries, electron and molecular. Now, electron geometry is really just based on the total number of electrons or electron groups, and molecular geometry is the description of the overall shape. So like, let's say electron geometry could be something known as tetrahedral, while molecular geometry is known as something like bent. So tetrahedral is telling you that there are four, tetra meaning four electron groups, and bent is really just describing the shape of that structure. But we'll dive into that. So to figure out how many electron groups in total you have, I have a formula here, and our electron groups are our bonds plus our lone pairs. And it's not the individual lone pairs, it is the pair itself. So we'll get into that, and we're actually going to get really, really into detail of every single type. You ready? All right. So our first type is linear. And I have an example of a linear structure so far. Now, I'm going to first start off with identifying the group, the overall electron groups. So I'm going to show this as electron groups. And we said that electron groups are our bonds plus our lone pairs. Now, specifically, this is going to be on your central atom. So in our case, beryllium, or Be, is our central atom for this Lewis structure. Now, we'll have, let's see, our lone pairs. So specifically, there are only two bonds, and there are no lone pairs on your central atom. So I'm going to say plus 0, and that's where I get this value, 2, number of, this is also saying electron dense areas. I want you to think electron groups. All right, so when it says electron dense areas or electron pairs or electron groups, they're all really just referring to how many electrons are surrounding that central atom. So this is just a simple little structure or representation of a linear electron geometry. All right, so that's our first part. And then also it's going to be the same exact thing for our molecular geometry. So we don't start till, like, whenever we start to change the amount of lone pairs on the central atom, that's when your molecular geometry will change. So in our case, since we haven't added any lone pairs, the molecular geometry will be the exact same as our electron geometry. Moving on. So now let's look at something that has 3 different electron groups. So in our case, let's start off with this first type. Boron is our central atom, and I'm going to count again. So I'm going to see how many bonds and lone pairs are on my central atom. So looking at our central atom, there's only 1, 2, 3, and there are no lone pairs. So in our case, our electron geometry is going to be known as Trigonal Planar, and our molecular geometry is also the same. It will be Trigonal Planar because there are no lone pairs on your central atom of boron. Now let's look at a different type. So let's say if we're comparing this to let's compare this to something that actually has lone pairs on your central atom. So in this case, we're going to have 1 and 2 bonds. Now I want to make a note here that I did not count the double bond as 2 bonds. Right? I only counted the double bond as 1 bond when we're trying to figure out our electron group. So in our case, we're only going to have 2 bonds, 2 double bonds, but they're still going to just count as 2 bonding groups or bonds, plus that lone pair on sulfur, which is our central atom. So in our case, our total electron groups would be that 3. So that's why in this case, the electron geometry would have been trigonal planar because there are 3 electron groups. However, now that we added a lone pair on our central atom, then it's known as bent for our molecular geometry. So that's that special case right there that we're seeing whenever we start to add lone pairs on the central atom, our molecular geometry will change. And we're going to keep seeing this. So let's try another one. And then I also wanted to make a note that for Vesper Theory is kind of that more of that 3D structure that I really kind of showed here with our bond angles. So that is something that you have to know. Let me go ahead and go back to Vesper Theory as a whole. So for linear, the overall structure is going to be 180 degrees. And that makes sense. It's just a perfect line, right? If we go back way back when to geometry, remember that a perfect line is going to be 180 degrees. Now that's the same concept here for linear. Makes sense why it's called geometry. If people ever ask, will I ever use this again? You are now, right? So in this case, also for trigonal planar, we're going to have different bond angles as well. So whenever we don't have any lone pairs, then we're just going to have, at least for trigonal planar, we're going to have 120 degrees as we see on this one. Now, when we start adding lone pairs on our central atom, then the bond angles will decrease. So in our case, we're going to say that it's now less than 120 degrees on this overall, this structure of bent for a trigonal planar electron geometry. So let me go back to what I'm trying to say here, and it'll make more sense once we see the structure. So now going back to the Vesper theory of this structure, remember that Vesper theory is just saying that electrons want to be, or atoms want to be as far away as possible because our electrons are going to repel and they don't want to be, by each other. So that's why I'm spacing everything out and it's actually symmetrical. So in our case, this would have been 120 degree angle all throughout. And that's Vesper theory. Now, I'm also going to show that with our bent structure here, where those lone pairs actually start to literally bend. Like I want you to think of it as like a weight. Those electrons tend to, like, let's say if this is our bond, right, then our electrons typically actually make it bend because it's sitting on top. So that's the concept there. So that's why it's a little bit less than 120 degrees. And we'll keep going. All right, so our other type is known as tetrahedral. Now, tetrahedral will have 4 electron groups on our central atom. So let's check that. We'll start with CH4, which is this example. And our electron groups, as mentioned before, are our bonds plus our lone pairs. And we're specifically focusing on the central atom. All right. So in our case, we're going to focus on carbon, and we're going to count how many bonds there are. So there is 1, 2, 3, and 4. So there's 4 bonds, but no lone pairs on carbon. So in our case, we would have an electron geometry of tetrahedral as well as a molecular geometry of tetrahedral. Now we'll continue on. Let's do another type. So in this case, on PCl3, we're going to have 1, 2, and 3 bonds. So 3 bonds. Plus there's 1 lone pair on our central atom of phosphorus, giving us 4 electron groups. So that's why this would have been 4. Now our electron geometry is going to be tetrahedral, because our electron geometry only focuses on the overall electrons surrounding our central atom. So that's why when we add those bonds plus those lone pairs from our central atom, that gave us 4. 4 electron groups tells us our electron geometry is tetrahedral. Now we just added 1 lone pair on our central atom. So in our case, we're no longer going to have a molecular geometry of tetrahedral. Instead, this is known as trigonal pyramidal. So as we keep adding more lone pairs, the name for the molecular geometry will change and it will not be the same as your electron geometry. Remember, the molecular geometry just focuses on the shape of the structure. It's a more, it's more descriptive overall, like let's say bent, right? You're later going to see something that's known as T-shaped, and it's really just telling you what type of shape this overall is. Now we'll keep going with this. Another example. On our central atom of sulfur, let's count those bonds again. So in our case, we're going to have 1 and 2. So we have 2 bonds. And then looking at our central atom of sulfur, we're going to have 1 and 2 lone pairs. So 2 plus 2 gives us 4 electron groups. So this would be an electron geometry of tetrahedral. But we added 2 lone pairs on our central atom, so the molecular geometry is known as bent, which makes sense, right? You can literally tell that the shape of this is bending. Those lone pairs are kind of just acting as a weight, and it starts to bend that bond just to make room because electrons, once again, are repelling against each other, and they don't want to be close to each other. So that's our Vesper theory, and I'm going to show you what all of these really look like. I also want to make a note that you're probably going to see a lot of these where you're going to have something that's wedged, which is this. So this is a wedged, and then this is a dashed line or bond. Now let's talk about just what in the world that means. So if something is wedged, that means it's coming towards you. All right, so it's coming right out of, I want you to think of out of the board or out of the page. It's literally just going towards you. Okay, now if something is dashed, you can't see it. It's behind something else or behind the other, like I would say, like this one is in the back and you really can't see it. So anytime there is a dashed bond, that is not in your eyesight or in your eye level, like you can't see it. Anything that is a solid line, you can see it. It is in your eyesight or eye line. And then anything that is wedged is literally coming right towards you. All right, is that making some sense, guys? So I could even kind of think about it this way. Here, I oftentimes do this with students. Now, let's look at it this way. This will make so much more sense. All right. Yay, Sharpies. So let's say we're doing something like, I'm going to go back to something like Trigonal Planar, and we have these 3 bonds, right? All right. So looking at this, it's a little bit tough to see, but there we go. Looking at this, I want you to think of the pink, this lighter pink coming towards you. So that's going to be wedged. Now, this next one, the blue that is right here, that's still in your eyesight, right? You can still see that now, or in your eye line. So you can still see that. So this would just be a single line. Now, you can barely see this hot pink, right? It's kind of hidden behind here. So that's going to be dashed. So anything that's kind of hiding in the back, like if we were to kind of move this, this is coming towards you, right? So that's going to be wedged. This is a solid line because you can still see it. And however, it's kind of hard to see all the way in the back, this hot pink Sharpie, that's going to be dashed. So that's kind of essentially what we're looking at with a 3D structure. Vesper is a way to draw a 3D structure 2D, right? So this is kind of like the easier way to look at it. And that's essentially what actually a lot of you guys probably have done with different 3D models or those kits that you have to work in lab. So continuing on with that concept, this is the proper way that you would actually draw a tetrahedral structure in Vesper Theory. Now, this is what it would look like, and everything's kind of nicely spaced apart. And as I mentioned, that wedge is coming towards you, that dash is going in the back. And this is another way of drawing trigonal pyramidal in Vesper Theory, just looking at it this way, where instead everything is now kind of making room for those lone pairs on top. And then lastly, I kind of drew this one in. The bent structure is once again having those 2 lone pairs on top, and that's making room and kind of bending the rest of that structure. So that is tetrahedral. Let's keep going. So I also want to make a note that some of you guys, depending on what class you're in, whether you're in high school, you might just stop at tetrahedral, or if you're in a kind of like a prep class, a chemistry prep class or introductory class, you might just stop here. As you continue with chemistry, you will see these next geometries. So depending on what major you are or just where you are along with chemistry, but we'll still get into that. Now, the next type is going to have 5 electron groups. Let's look at that. So our electron groups, in our case, let's focus on this first compound, or Lewis structure. And looking at our central atom of phosphorus, let's count how many bonds there are. So remember, electron groups, I'm going to keep repeating this, are bonds plus our lone pairs. And then if at any point you guys have any questions, go ahead and leave them in the chat, or you can literally ask a question and I will answer that. I definitely see that. There's a button that says on the screen, ask a question, and I will be happy to answer your guys' question. Another thing, by the way, as more and more people come and join the session, definitely need help with overall. So next week's tutoring session is to be announced just because I want to know what you guys need. These sessions are really designed for you. So please in the chat, let me know what you're still struggling on, and I will help you out and we can talk about that next Sunday. All right, so continuing on with this, let's look at our central atom of phosphorus, and we'll see that we have 1, 2, 3, 4, and 5 electron groups, or bonds in general. 5 bonds because there are no lone pairs on your central atom. So in our case, we're going to have 5 electron groups, and the electron geometry is going to be trigonal bipyramidal. All right. Then now, since there are no lone pairs, the molecular geometry will be the exact same as our electron geometry. So it's also trigonal bipyramidal. Now, let's keep going with a different type. There's several different types of these. Now, let's look at the next compound, or the next fluid structure. And we'll focus on sulfur as our central atom, counting our bonds, 1, 2, 3, and 4. So we have 4 bonds, plus there is only 1 lone pair on our central atom. So that gives us still 5 electron groups, making it an electron geometry of trigonal bipyramidal. Now, if we add 1 lone pair, then it falls under this category. And I've oftentimes seen it as seesaw. In some books, it could also be known as sawhorse. Who comes up with these, right? Now, seesaw is really kind of just showing the overall shape that supposedly looks like a seesaw. Now, if we were to see that in Vesper Theory, this is kind of what it would look like, where your lone pair on that central atom is here. And once again, that's dashed, meaning we can't see it, right? It's hidden in the back. And then here we'll see that this fluorine is coming right towards you, right at you. And then this fluorine is hidden in the back as well. And then these 2 fluorines on top are in your eye line or in your eyesight, so you can definitely see those. So in that case, as I mentioned, our electron geometry for that case would have been trigonal bipyramidal, but our molecular geometry, since we added 1 lone pair, would be known as seesaw or sawhorse. Okay. Now, continuing on, there's another type. There's so many types. Now, I'm going to look at this structure and count how many bonds again. And bromine is our central atom, so we'll count 1, 2, and 3 bonds. Our lone pairs on our central atom are 1 and 2. So we still have 5 electron groups. So once again, our electron geometry is going to be trigonal bipyramidal. However, since we added 2 lone pairs on our central atom, that is known as T-shaped. So T-shaped, if we were to draw this as our Vesper theory, it literally looks like a T, right? Literally looks like a T. So that's why they're defining it as that. And that's kind of another thing why I keep saying that molecular geometry is really describing the shape of the structure. And this is the best, example to really show that, yes, it really does look like a T. All right, continuing on. Let's look at xenon. And that's our central atom. We'll have 1 and 2 bonds on our central atom. But looking at how many lone pairs, we have 1, 2, and 3. So we still have 5 electron groups, because remember, electron groups are our bonds plus our lone pairs. And in our case, we said we had 2 bonds plus 3 of our lone pairs, giving us 5 electron groups. So still going with this concept that it has 5 electron groups, our electron geometry would then be trigonal bipyramidal, and then our overall molecular geometry would be known as linear. And that's just because there are 3 lone pairs on your central atom. All right, there's one more. There's one more. Goodness. All right. This next group is known as octahedral. All right. So an octahedral just means that there are 6, and I know that's kind of deceiving, right? Octa typically means 8, but in our case, octahedral is going to refer to 6 electron groups overall. So in our first case, we'll see that sulfur has 6 bonds altogether, and we'll count that. So on our essential group, there's 1, 2, 3, 4, and 5, and 6. So right then and there, our electron geometry would have been octahedral. There are no lone pairs on your central atom, making it octahedral for your molecular geometry. And then now we'll add some lone pairs to change our molecular geometry. So in our case, we'll see for our next structure that iodine is our essential atom. All right, let's count those bonds. So 1 and 2, 3, 4, and 5. There are 5 bonds plus the 1 lone pair, making it 6 electron groups. So our electron geometry would be octahedral. Now we added 1 lone pair. So now we have a different type of molecular geometry, which is square pyramidal. And we'll keep going. And then just to kind of show this again, this is the overall Vesper theory. Once more, I'm going to go back to all of the different bond angles. So several different teachers or professors will tell you that you do have to remember them. I'll teach you kind of a trick as to how to remember all of your bond angles, just so you don't have to memorize every single one. And then in our case, let's keep going. Our next structure, looking at bromine, we're going to have 1, 2, 3, 4, 5 bonds again. 5 bonds and only 1 lone pair. So that's just another example of square pyramidal. And we see that because there are 5 bonds and there's 1 lone pair on your central atom of bromine. And we'll keep going. So the next, for xenon, we'll count how many bonds we have in total. We have 1, 2, 3, and 4 bonds, and we have 2 lone pairs on our central atom. So looking back at that, whenever we have 6 electron groups, we're going to have an electron geometry of octahedral, but our molecular geometry will change because we added 2 lone pairs on our central atom. So in our case, it's known as square planar. So this is an example of square planar, and this is what it would look like as our Vesper theory. All right. And as mentioned, let me know if you guys have any questions at any point. And I'm going to go back to just the Vesper theory, and then we'll get into polarity. All right. So for Vesper theory, a lot of times you will have to know all the bond angles. And it's not as bad as it seems. So everything is ordered depending on the electron groups. And as I mentioned, we have something like, whether it's 2, 3, 4 electron groups, 5, or 6. And we mentioned that 2 would have been typically linear. And I'm just talking about the electron geometries at the moment. And 3 electron groups would have been trigonal planar. And 4 would have been tetrahedral. 5, trigonal bipyramidal. And then 6 would have been octahedral. So in our case, I kind of want you to think of these as like little groups or little families. Okay, so everything that only has 2 electron groups is going to have 180 degrees overall. Anything that has 3 electron groups will have something around 120 degrees. Now, if there are lone pairs on your central atom, then it would be less than 120 degrees for those that have 3 electron groups. All right, following me a little bit? So now I'm going to go to the next type. And then if it's tetrahedral, meaning that it's going to be 4 different electron groups, then it is typically 109 degrees for your bond angle. However, when we start adding lone pairs like these 2, that means it's going to be less than 109 degrees. So anytime you are adding lone pairs on your central atom, that is going to be less than the typical bond angle of that group. And we'll keep going and we'll keep seeing that. So now for trigonal bipyramidal, this is where it's a little bit different, where we're going to have something known as axial and equatorial. Now, all this is really saying is, and I'll zoom in for this, is these that are perfectly 90 degrees, as we can see here, these are all 90 degrees. Those are known as axial. Okay, so think of it kind of like axial, like maybe like the y-axis, right? Going back to math, that's maybe something that we can remember. Equatorial would have then been those on the side, making it more of 120 degrees. And this is specifically for are 5 electron groups where we would have 90 degrees and 120 typically. Now for octahedral, you're going to typically have 90 degrees all throughout because that's just how you're able to space everything symmetrical. And then we'll see that here. So however, when we start to add lone pairs, as I mentioned, that's where we get that less than 90 degrees, right? Because typically octahedral will have 90 degrees with the, and that's overall, that's kind of the main concept here is every single time you'll see those lone pairs kind of scrunching it together, you will have less than 90 degrees. All right, so that was a quick little trick to how to remember all of your bond angles. As I mentioned before, that depending on what electron group it's in, it would be like, let's say, I'm going to go over this real quick again, that this first one would have been 180 degrees. Then the third one, trigonal planar, or with 3 electron groups, that would have been 120. Add a lone pair, it's less than 120. Same thing with tetrahedral. It's typically 109. And then add a lone pair, it's less than 109. Those are your typical ones. Everything thereafter, as we mentioned with 5 electron groups, would have been 120 and 90 degrees. 90 degrees on your axial, and then 120 on your equatorial. All right. And then octahedral, as I mentioned, would have been 90 degrees or less if we add a lone pair. Now let's jump into the concept of polarity. I know this is a big concept. You will continue to see polarity and overall just the concept as a whole. Polarity is really going to focus mostly on the concept of electronegativity. And electronegativity is really just how attractive the atom is, meaning how can this atom attract other electrons? Okay, and there are more attractive atoms in our periodic table, or elements in our periodic table. And as you can see here, this is the overall electronegativity trend. Now, I also included the values specifically of the electronegativity on each, that you can kind of compare the values. So essentially what this is saying is that we will increase as we move to the left of the periodic table, and then I said left, to the right of the periodic table, and as we go up in the periodic table, it will increase as shown by the arrows here. And then I also highlighted your most electronegative atom, which is fluorine. So at any point, if you're forgetting, what's the trend for electronegativity, I want you to think of whatever is closest to fluorine is then the most electronegative. All right. And then we'll see that here, that a lot of times students think that I'm not sure, is oxygen or chlorine more electronegative if I'm comparing those two. And it's actually oxygen. So oxygen would have been a lot more electronegative versus chlorine. And you can tell that by the actual values. That's kind of something to note, is that really the higher up it is, and especially like that's really right next to fluorine rather than being under fluorine, that would then be more electronegative, as you can tell. But we'll go over this. Now, how does this tie into polarity? Good question. Good question. Let's say if we were to have something like HF. In our case, we're going to compare our overall polarities as a whole. Now, polarity, I want you to think of it like a tug of war. All right. So if we're looking at this, let's go back to that table. For polarity, the most electronegative atom wins the tug of war. Okay, so I want you to think of it as, let's say anything that is like furthest away from fluorine is going to be very weak. All right. So think of someone who just isn't strong. All right. And then rather fluorine is like a bodybuilder. All right. Can you get that visual in your mind? All right. So in that case, if we were to go back to this and we're looking at that tug of war, who's going to win that tug of war? Fluorine would, because fluorine is a lot more electronegative or a lot stronger. And then this is what's known as a dipole moment. So a dipole moment is that idea of the tug of war, where in our case, it's really just a pool of electrons. So as we mentioned, electronegativity is how attractive that atom is to other electrons. So In our case, since fluorine is the most electronegative in this case, it will pull or win that tug of war and create a dipole moment, which is really just a pool of electrons. Okay, so that's kind of what I'm kind of initiating or trying to have you think about. Now, there are also other things relative to polarity. We're also going to get into symmetry and how that can change, and we'll get into that. So just keep thinking about that concept that everything that is closest to fluorine is more electronegative. So I want you to think they're really, really strong. They're bodybuilders up in this little area. And then everything thereafter is just weak. All right. So always kind of think of that, tug of war, like who's going to win that tug of war overall. So we'll keep going with that. And we'll do a bunch of examples. Now, this table is really, really helpful because this is talking about whether just the overall molecular geometry or molecular shape is going to make it polar or non-polar. And we'll go over a ridiculous amount of examples for us to really understand this concept. All right. So let's kind of just look at this overall, where our first type would have been linear. And then what this chart is trying to say is that anything that's linear, meaning that we would actually have only two bonds on our central atom. Remember that? So if we have two bonds on our central atom or two electron groups on our central atom, then and if they're connected to the same exact atom, then it would be non-polar. And the concept here is because if we were to, let's actually look at an example. This is a perfect example. Carbon dioxide. So if we were to look at the Lewis structure of carbon dioxide and look at this as, we know that oxygen is very electronegative because it's right next to fluorine on our periodic table. So since it's very electronegative, I want you to think of this as, they're the bodybuilders again, or they're really strong. And we're trying to compare and see who's going to win that fight or who's going to win that tug of war. Now, in our case, since they're both oxygen, they're both the same strength on equal sides, or the same atoms on equal sides, they're going to cancel each other out. So if something is symmetrical, it would be non-polar. Yes, did you catch that? So anything that is symmetrical will be non-polar. Something that is not symmetrical will be polar. All right. So that's something to definitely know. And we'll get into all these different concepts. Continuing on. So what would happen here is our oxygen would pull one way. The other oxygen would pull the other way. And essentially, there would be no dipole moment, meaning no one wins that tug of war. It's an equal pool of electrons. So they just end up kind of going nowhere. And that's why this would have been non-polar, because there is no dipole moment. And then I realized that Juan asked a question, and he asked how to determine polarity of our geometrical shapes for Vesper theory. And I'm answering that right now. We're going over that completely right now. And we'll keep doing more examples. So let's say if we had this other example of HCN. Now there are two completely different atoms on either side, right? Yet this is still linear. And we'll notice this. This is linear because there are only two electron groups, right? Let's go back to that concept. So electron groups are our bonds plus our lone pairs. So in our case, we're not going to count that triple bond as three bonds. We're only going to count it as one. All right. So in our case, we only have two bonds, and it's linear. And that's going to look like what this table is saying. Whenever we have totally different atoms on opposite sides, then it's no longer symmetrical because they're different atoms. Then that would most likely be polar. And we'll see that. So going back to this structure, think about that tug of war once more, where nitrogen, and let's actually go back to our electron negativity, and nitrogen has an electronegativity of 3, yet hydrogen has 2.1. So nitrogen would be stronger, right? It's a lot more electronegative. So that's why it would win that tug of war. So in our case, hydrogen would not be able to compete with nitrogen's pull of electrons. So that's why this structure would have a dipole moment. So once again, dipole moment just means that it's a pool of electrons, that they don't cancel each other out, and that someone wins that tug of war. And in our case, this would be polar. So that's a good example of that. And we'll keep going. And then now looking at the next type of structure, which our molecular geometry would have been bent. And this bent shape is referring to, and it doesn't show it here, is referring to there being some sort of lone pairs on that central atom overall. And in our case, let's go ahead and do something like water. This is a very good example. You're going to keep seeing this example, so definitely know the structure of water. Now, if we're looking at water, let's go ahead and kind of practice also doing our electron geometry as well as our molecular geometry. So let's figure out our electron groups as a whole. So electron groups, let's add those bonds on our central atom of oxygen, which is 1 and 2. And then we'll have 2 lone pairs on our central atom of oxygen. So right then and there, if we count this 1, 2, 3, and 4, we'll have 4 different electron groups. 4 electron groups would then give us an electron geometry of tetrahedral, but our molecular geometry, as we just said before, was bent because there are 2 lone pairs on our central atom. So since this is bent, what would happen because of those lone pairs, it would actually make it very electronegative, or it would make it polar because, and even just looking at the atoms as a whole, I want you to see that oxygen, as we said, was very electronegative. Hydrogen is not. So what would happen, our dipole moment, or who would win the tug of war, it would look like this. And then what I'm drawing is really just, I'm showing this as a dipole moment. That's what that arrow signifies. That arrow is just telling you where is the pool of electrons that we're going to see. And this would have been our dipole moment as a whole. And then another way that you can also see this is you can see that hydrogen would have been pulling the opposite direction, and it's really small because it's very weak. And then the reason why I'm drawing the arrow even larger is because I'm showing that oxygen would win, and that's where the overall dipole moment would be, because oxygen would win that tug of war. I'm going to keep referring to that. And in our case, this would be very polar. So water is very, very polar. So that concept will continue on and on when you guys get further on in chemistry, actually this semester, this school year, when you guys get into solutions or things like that, and I'll touch on that again. So another thing to mention is typically when you have lone pairs on your central atom, that adds to polarity, or that adds to that electronegativity. I want you to think that a lot of times with lone pairs that are on your central atom, that will make your structure polar. Typically, all right, I don't want to say always with chemistry, but typically those lone pairs on your central atom will make your compound or your structure polar. And we'll still keep going with these examples. So that kind of went back to this bent shape where it's always going to be polar. Now let's look at our other types of molecular shape or structure, and we're going to see something like trigonal planar. Now, if we were to have the exact same atoms all throughout and it's all consistent, then we said that something that is symmetrical would be nonpolar, right? Anything that has symmetry or is symmetrical is nonpolar. Something that is not symmetrical will most likely be polar. So in our case, let's do another example like that. Here we have trigonal planar. How do we know that? Because there are 3 bonds or electron groups on your central atom. That gives us trigonal planar. Now going back to this, though chlorine is relatively electronegative, I would say. Now it's going to be strong, so everything is going to pull in opposite directions. And because these are perfectly spaced out, as we said, 120 degrees, all of these would cancel each other out. And think about it is if we were to have that tug of war, that rope, and we're pulling this all in the exact degree where everything is symmetrical with each other, and it's the exact same bodybuilder or the exact same person pulling that rope, no one would win, right? They would get exhausted and then just say, we're done. But no one would win because no one wins that tug of war since it's symmetrical and since it's all equal pulls all throughout. So since there is no dipole moment or pull of electrons, then we would say that this is nonpolar. So anytime we have a compound that is trigonal planar and all of the atoms surrounding, which we're saying here, chlorine, chlorine, and chlorine, since all of them are symmetrical or all throughout our chlorine, it would be nonpolar. And then let's see what else we can say. That was tetrahedral. All right. However, if we were to then say something else that was trigonal planar, but it was no longer symmetrical, and let me see if I even have, I think I have an example of that. I do. Perfect. Here it is. So let's compare this one, and let's see that this is trigonal planar. Once again, we know that because this is 1, 2, and 3 bonds or electron groups on your central atom. And since this is trigonal planar, we can tell that we said that fluorine was the most electronegative atom, so it's the stronger one. So in our case, fluorine would pull on that direction, and then hydrogen is very, very weak in electronegativity. So doesn't really do much. So in our case, the one that would win, or the dipole moment or pull of electrons, would be on fluorine. So right then and there, and what I'm signifying here overall is really just the concept that this is where our pull of electrons would be. Our fluorine, since they're on opposite sides, and though everything is symmetrical, our fluorine would pull in one direction and it would actually be polar in this case. So it really does depend on symmetry. It also depends on electronegativity when we're looking at polarity. And we'll keep going with these concepts. And then symmetry, I'm really talking about these different types of geometries. Now, we just went over that trigonal planar. And whenever we have two of the same atoms, but the last atom is not the same, that would give us something that is polar. Now, our next two cases are going to be tetrahedral. I did include other larger electron group structures just so we can practice that as well. So our next one is a tetrahedral structure. Remember, tetrahedral has 4 electron groups. And then in our case, if it's symmetrical again, then that means it's nonpolar. So if we were to have all of these atoms being the exact same atom, they would cancel each other out because they're symmetrical and they're all the same. So let's look at an example of that. So let's say if we had this, going back to the structure of CH4, hydrogen really does nothing. And I wanted to include this case because this is actually known as a hydrocarbon. What's a hydrocarbon? A hydrocarbon is a compound that consists of only hydrogen and carbon, which is this one, right? This only contains, this is CH4, this only contains hydrogen and carbon. So this is CH4, hydrocarbons. All hydrocarbons are nonpolar. Nonpolar, that's something to definitely note whenever you just see any sort of Lewis structure that only has hydrogen and carbons throughout, nothing else, then that will be nonpolar. And then we also see that here that even though they're all pulling opposite directions, they all have very, very small electronegativity because hydrogen doesn't really have much electronegativity. And then we'll see here that everything is pulling in the opposite but symmetrical way, and no one wins that tug of war. So once again, this is nonpolar. And we'll keep going with this. Our next one is tetrahedral once again. It's going to be polar. And the reason why it's going to be polar is because we no longer have that symmetry. Here you'll see that there are 3 different types, or sometimes even 2 and 2, but they're not all the same atom is what I essentially want to say, is that though it's tetrahedral, they're not all going to be the exact same atom. This is the one exception that I will say with symmetry. And we focus on electronegativity. So you could draw this structure a few different ways. You can draw this structure, and I'm going to say like this would have been CH2Cl2. So you can draw this structure a different way where we rearrange our chlorine and our hydrogen to look like this, right? So in our case, if we rearrange this compound or this fluid structure in this second form, that would have then, applied to the rule of it being symmetrical. And in that case, then being nonpolar, because these 2 chlorine would then pull in opposite directions and canceling each other out. And that's what you would think, and you would write nonpolar, but sadly that would be wrong. So in our case, it's a little bit different here because of the possibility of drawing this other structure as this other way where we're gonna put the chlorines on the opposite side. So we're gonna put the chlorines here and hydrogens on the other side. We said that hydrogen is not electronegative whatsoever, but chlorine is. So in our case, I still want you to think of that tug of war, and chlorine would be pulling in this direction, but hydrogen would then be pulling the opposite direction, but doesn't really do much because it's not very electronegative. So in our case, who would win the tug of war, or that pool of electrons would have been the chlorine. So in our case, this would have been polar. So beware of that. If you see anything that maybe it seems like it's going to be symmetrical, but you can draw it a different way to make it polar, then it has a possibility of being polar. Right, so it does depend on how it is you draw that Lewis structure. So definitely practice those Lewis structures. And I would also say, don't just stop there and think that, like, let's say if you were to just see the overall structure or the overall formula, chemical formula, and you saw this and you said, you know what, it has an equal amount of atoms surrounding that central atom of carbon. It has 2 hydrogen and 2 chlorine. That has to be symmetrical, so it's nonpolar. Don't do that. To really, really guarantee that you get the answer right, I really recommend you to actually draw out the Lewis structure, and specifically just really like comparing it, and as I mentioned, really see if there's any other way that you can also draw the Lewis structure that might make the atom polar, especially in this case, especially in tetrahedral in that scenario. All right, so for sure, draw out the structure. Let's keep going. All right, so there's another type of tetrahedral, and we'll see that here. And then this is going back to just looking at that lone pair on that central atom of nitrogen. All right, so in our case, this might seem to be polar or nonpolar. So if we were to look at it, maybe you might have drawn this a little bit differently, and you would have thought that, you know what, this might be, here. If you were to have said that this is probably something like this, and you were to then say, okay, well, everything is pretty symmetrical. If I were to chop this right along the middle, and yeah, that seems to be nonpolar because it's symmetrical, not the case. So in our case, whenever, as I mentioned, whenever we add those lone pairs to our central atom, it then makes it polar. All right, so how I have it drawn above right here is the proper way. So another thing too is if you really can't tell from looking at the drawing or the Lewis structure, try to draw it as a Vesper in Vesper theory overall to see how everything is just angled. Because whenever we put a lone pair, as we mentioned before, these bond angles will then decrease. So before, as I mentioned, anything that is tetrahedral, as we saw here, those bond angles would have been 109 degrees. However, when we start to add those lone pairs, it's less than 109 degrees. And it's just because these lone pairs are starting to kind of push the other. Like, I really want you to think of it as it's pushing or bending just to make room for those lone pairs, because once again, those electrons are repelling each other and they need to have that extra space. So in our case, this would have been polar because fluorine is very electronegative. It's actually the most electronegative. And then fluorine is pulling in this direction. All right. And this is not symmetrical because the nitrogen is pulling in the opposite direction. And then who's going to win? Well, the fluorine's going to win because it's going to really pull in that direction. However, nitrogen is still adding and still putting up a fair fight. But because it is not equal, it's not an equal pool of electrons, they wouldn't cancel each other out. All right, so that's another concept to really think about, is if they have that imbalance where it's literally they're going back and forth, or one would just instantly kind of win that tug of war, which in our case is fluorine, then we can see that, okay, that's a possibility. Another thing that actually we could have even seen is just looking back at those lone pairs and just said, okay, well, that's going to add to polarity. So right then and there, I can say it's going to be polar. So definitely watch out for that. And then we'll see a couple other types. And once again, this is now going back to symmetry. So let's just focus on something like this. And this is going to be trigonal bipyramidal because there are 1, 2, 3, 4, and 5 overall bonds or electron groups on our central atom of phosphorus. So in our case, if we see that it's symmetrical, which we do, everything is perfectly aligned. And I know this is kind of hard to see, but it would have been aligned. Everything is pulling in opposite directions. And no one wins that tug of war, or there are no unequal pools of electron. This is really, once again, going to be nonpolar. And these are just great representations of these. Another kind of concept here would have been, let's say, if we had something that was octahedral, then going back to these types of structures, something like this, all throughout. Then once again, because this is symmetrical, right then and there, we can just instantly tell it is nonpolar. All right, is this making sense? We can keep going back to other types. We have a little bit of time left. And if at any point, does anyone have any questions, leave in the chat. Let me know if you have any questions that you want me to go over. And also let me know what you want me to cover next week at any point. Leave a comment below or a chat in the chat. Definitely let me know. And I'm going to keep going with just these other types that we've saw before. All right, so we got back to something like this, and let's just practice doing a few of these. All right. So going back to these, let's just kind of look at, will this be polar? Would this be nonpolar? And focusing on this structure, because there is a lone pair on that central atom of phosphorus, boom, polar. Because of that lone pair, overall, we can then say, okay, that's going to add to our electron pool, and then therefore it would be polar. So anytime we really see those lone pairs on our central atom, that adds to polarity, polar as a whole. Now I'm going to keep going to another type and looking at this one, and we'll see that, okay, if we have 2 lone pairs on sulfur, and then also even just looking at hydrogen as a whole, we said that that's very, very small, and that's not really going to do much at all. So in our case, hydrogen is weak, as we said before, in electronegativity, so that will barely pull anything. And sulfur, because it has those 2 lone pairs and it is more electronegative than hydrogen, would pull in that direction, causing a dipole moment, which we said was just a pool of electrons. This would then be polar. All right, let's do a few more. All right, let's see what else you can look at. This is a good one. So let's go back to this one. And let's check and see what this would have been. So we mentioned before that this was a molecular geometry of bent. And once again, we have those lone pairs. And even though oxygen is very electronegative and it's pulling in this direction, because of those lone pairs, we're going to have a dipole moment, and that will add to polarity as a whole, making it polar. We're going to keep seeing stuff like that. So we really mentioned that trigonal planar, when all of the atoms surrounding are the exact same, they would cancel each other out, making it non-polar. And we covered that. And then going back to this one, remember that anything that's linear and it has that symmetry, and there are no lone pairs whatsoever, making it non-polar. Making sense? Let's do another type that I mentioned, since we have a little bit more time. Let's say I were to construct this crazy looking structure. And if we were to look at something like this and just think, what in the world's going on? There are two central atoms, it's carbon and carbon. I have no idea if it's polar or non-polar. Remember that hint that I told you that anything that is a hydrocarbon, right? Hydrocarbon, meaning it only consists of hydrogen and carbon, makes it non-polar. Non-polar. Right then and there, anything that only consists of hydrogen and carbon makes it non-polar. All right, guys. So thank you so much for tuning in and joining everything. Definitely let me know in the chat what you want me to go over next Sunday, and I will be, letting you know what I'm going to be going over as a whole. Another thing is, please help me get to 10,000 subscribers. When we get to that 10,000 subscriber mark, then what I will be doing is an 8-hour live tutoring session. 8 hours, I know. So an 8-hour live tutoring session before your finals, just to really help you guys out so you don't have to stress so much and can really get these concepts down and just refresh your memory on everything. You can also then use that time to ask me questions, and we can really just study and work on these concepts together. So share my videos. I definitely let other people know about just me in general, my channel, anyone that you can think of that will benefit from these chemistry videos, anyone in your chemistry class, teachers, and so on. So thank you so much, guys, for being here, and I will see you next Sunday. Take care.